Hello and welcome to this lecture on finite state machines that falls under the Automata and Theory of Computation course. This particular lecture will be on the fundamental concepts of FSM, that is the finite state machines. Besides, I'll try to demonstrate a simple trick on solving problems related to state machines. Before we proceed to our main discussion, let us have a brief intro about these machines. Well, the FSMs are devised to represent the abstract form of languages. To understand the language, we need to gather a couple of other ideas. We'll start with alphabet. As we all know, alphabet is nothing but a collection of symbols. In automata, we usually denote alphabet by sigma. The next concept would be on string, which is the sequence of alphabets. So, if we have our alphabet set sigma with two elements, that is A and B, then sigma closure will give us all the strings over A and B using all possible combinations. Now, if we put some restriction on the strings, we'll get a language. So, language can be defined as a structured collection of strings with certain conditions. The number of elements in a language can be finite as well as infinite. Now, if you'd like to construct all the strings from English language, we can do that considering our alphabet set A to Z, the 26 Latin symbols. Now, we'd like to visualize the working environment for the FSM using a block diagram. Since this automaton will determine whether a string belongs to a language or not, thus the machine will take the string as its input and read only one input alphabet at a time. As this machine works in states, transition among the states are governed by the formation principle of the language. Once the entire input is read, the machine decides whether to accept the input or not. Well, the finite state machines are of two types: deterministic finite state machine, that is the DFA, and non-deterministic finite state machine, that is the NFA. In this particular lecture, we'll only focus on the deterministic finite state machine, that is the deterministic finite automata DFA. Now let us see the formal definition for the DFA. To define a DFA formally, we need to use 5 tuples. These are sigma, q, q0, f, and del. Sigma represents the set of input symbols, q for set of finite state, q0 is the starting state, f is the set of accepting states, and del is the transition function of the DFA. When it comes to the graphical representation of the DFA, the convention is quite straightforward. Hence, the DFA will be represented by a directed graph where each state is represented by a node, that is a circle. Edges show the transition from one state to another. Each arrow is labeled with the input symbol that triggers the transition. Moreover, we will add an open arrow to the starting state and we'll have double arrow for the accepting states. Furthermore, we are required to bear in mind a couple of important rules while designing DFA. In a deterministic automaton, every state must have exactly one transition for any input symbol, and all the states should have transitions for all input symbols. Let us consider this example where we are required to build a DFA that will accept all strings over A to Z starting with the symbol A. We'll start the DFA with our starting state, and for this particular case, state 1 is the starting state. So now we need to identify the smallest or the simplest string from this language. Looking at the problem, we can say the string containing only one A is the smallest one. So from state 1, reading input symbol A, we'll go to state 2. Since A is a valid string, so we mark state 2 as an accepting state. However, in state 1, we have considered transition for only one input symbol, where our alphabet set contains 26 symbols. So in the starting state, if we read symbols ranging from B to Z, we can say that the string is not starting with an A. Thus, for B to Z, we go to another state 3. So in C, regardless what is the input, we can always say the string is not accepted as we reach C reading a non-A symbol at the beginning of the string. Hence, we have a self loop in state C. Similarly, if you see that in state B, we are also having a self loop. This is because once we reach B, we can assure the string is going to be accepted.